In this video, we will talk about potential energy and conservative forces. Now, in particular, we will talk about gravitational potential energy and elastic or spring potential energy. We will also explore how these potential energies are related to forces. So in the case of gravitational potential energy, the force will be the gravitational force or the weight. In the case of elastic potential energy or the spring potential energy, the corresponding force will be the spring force described by Hooke's law. Finally, we will solve some problems based on the materials discussed. Potential energy is a type of mechanical energy, just like kinetic energy is a type of mechanical energy. Now, potential energy is associated, it's a type of energy that is associated with position of an object. Just like kinetic energy is a type of mechanical energy that's associated with speed of an object. So this position of an object means coordinates or positions, x, y, etc. So potential energy is actually a function of position or coordinates. And this is how we write them. U as a function of x, u as a function of y, and so on. Another thing is that potential energy is a scalar, just like any other type of energy, and it is quantified in the unit of joules with an abbreviation capital J. Let's first look at gravitational potential energy. Now we know it's associated with position, and indeed it is associated with position of an object in gravitational field, such as an object shown here, an object with mass m at a height of h meters from the ground. Let's first set up a coordinate system. So we will take the y-axis is going up, so this is the origin coincides with the ground. Now before we write down the expression for the potential energy, the gravitational potential energy of this object, we have to set the 0 joule level first. So we have a certain amount of freedom to do so, and usually it is a convention to set the ground level to be where the potential energy is 0 joules. Now once you set the 0 joule level, all the other levels are fixed automatically, and you can no longer set them to an arbitrary value. So what is the potential energy for this object? So the gravitational potential energy here of this object at such a height, y equals to h, is given by the following. U sub g equals mass of the object times the gravitational acceleration times the height of the object above the ground. So of course for Earth, g is 9.81 meter per second squared. So this is the potential energy of this mass at that height. So let's say the object drops all the way to the ground. What is the change of the gravitational potential energy of this object? Now the change, as any other change, is given by the final value of the potential energy minus the initial value. The final value is the value of the potential energy at the floor or the ground where it drops, so that is 0. And the initial value is the value of the potential energy at that height, which is mgh. So as you can see, as the object falls, the potential energy actually decreases as it should. Now, let's look at the same system slightly differently. Now, I have chosen the 0 level for the potential energy at height y equals to capital H. So this height is the 0 joule level. That means the ground level now will have to be less than 0. And indeed, it's given by minus mass times gravity times the difference in the height between the 0 joule level and the ground. So what this U means is that if this object here is here, the potential energy of the object is given by that. And the potential energy of this object here, the position of the object is still the same as before, namely the coordinate, the y coordinate is y equals to h, as shown here. So the expression for the potential energy is given by m times gravity times this height. So what is this height? Little h minus capital H is that distance right there. So little h minus capital H. And since the 0 level is at capital H, this factor here enters the equation as shown. So you see the absolute value for the gravitational potential energy looks a little bit different from the one that we showed before when the ground level was chosen to be the 0 joules level. Now let's assume this object drops all the way to the ground, and we want to calculate the change in the object's potential energy as it drops. So the change in potential energy is the final potential energy minus the initial potential energy. Now the final potential energy is the potential energy of the object when it gets there. So that is just minus mg capital H. And the initial potential energy is the potential energy of the object when it's there. And that is mg little h minus mg capital H. Now as you can see, these terms will cancel, leaving you with the same answer as before, minus mg little h. So the change in potential energy will remain the same, doesn't matter where we choose the 0 level for the potential energy to be, because it is the change in the potential energy that controls the physics and not the absolute value of the potential energy. Let's look at the elastic of the spring potential energy. What you have here in this diagram is a spring with a spring constant K, and the state of the spring is relaxed, which means the length is relaxed. So when the length is relaxed, the spring potential energy is 0. So that's how we define the 0 level for the elastic or the spring potential energy. When the spring is not compressed or stretched, its potential energy is 0. Now let's say we pull this object to the right, stretching the spring by an amount of x1. Now in this case, the potential energy of that spring will increase to half times the spring constant times the square of the stretch. Now it doesn't matter whether you stretch or compress, this is the equation that reflects the change in potential energy of the spring. So generally, if the spring stretches, say by an amount of x, its elastic potential energy will be given by that, half times k times the square of the stretch. Now let's look at how the gravitational force is related to gravitational potential energy. Now let's say you have a mass here above a ground, and let's say at a height of y from the ground. Now we know that the force that acts on this mass is its weight, or the gravitational force, Fg. And this expression Fg is given by, in vector form, as minus m times gravitational acceleration times j hat, because it's heading downward. And if you take the y-axis to be upward, then the weight is in the direction of minus j hat. A few minutes ago, we also said if we take the potential energy at the ground to be 0 joules, then the potential energy, the gravitational potential energy of this mass here at that height is given by simply m times gravity times that height. Now when you compare these two expressions, immediately you see that the gravitational force can be expressed as minus y derivative of that potential energy function, with of course the J hat there. So in this example, the force is related to the potential energy function like that. The same thing happens with the elastic or the spring force. The spring force is given by this Hooke's law that we have seen in one of our previous videos. And the potential energy, the spring potential energy, is given by that. Now when you connect these two expressions, you see that the spring force can be expressed as minus x derivative of that potential energy function with the I hat, because now x is the axis involved and the unit vector along the positive x-axis is I hat. And you see a connection between the force and the potential energy function. So such a force Fx that is related to a potential energy function Ux in this manner is known as a conservative force. So gravitational force and spring force are examples of conservative forces. Let's look at the following problem on gravitational potential energy. A mass 2 kg is dropped vertically downward from a building to the ground 10 meters below. If the object is caught by someone at a height of 2 meters here, calculate the change in potential energy of the mass during the drop by first taking the 0 joule level at the ground level and then taking the ground level to be the 10 joule level. So for part A, the change in the potential energy is the final potential energy, which means the potential energy at 2 meter height minus the initial potential energy at the 10 meter height. So at 2 meters, the potential energy is given by m times gravitational acceleration times 2. And U10 is mg10. Now because m is 2, so 2 times gravity times 2 minus 2 times gravity times 10. And that will give you minus 157 joules. Now we want to repeat the calculation, but now here the ground level is 10 joules. It's no longer 0 joules. So all the subsequent levels are raised by 10 joules. So again, the change in potential energy is given by the final potential energy U2 minus the initial potential energy U10. The final potential energy is mg times 2, but now you have to add 10 because all the levels are added by 10 joules, minus U10 is mg 10 plus 10. So the 10 goes away, and you see you get the same answer as before, which is minus 157 joules. So this is an example where the change in potential energy is not dependent on what we choose for the energy of the ground level. Now the problem, of force of 1200 newtons stretches a spring by 0.1 m. Calculate the spring potential energy when it's stretched by that amount. So first we calculate the spring constant from F equals to kx, that's the Hooke's law. So 1200 newtons is the force, k we don't know, 0.1 is the stretch, so that's going to give you k as 12,000 Newton per meter. Now using the expression for the spring potential energy, since we already know what k is 12,000, and the stretch is 0.1, square that, and you're going to end up with 60 joules. If the spring were to compress by the same amount, then the spring potential energy would still be 60 joules, because in both cases, the change in length is still 0.1 meter. Thank you for watching.